One, I apologize for not getting this video immediately after the first one. I've been fighting a cold, running some high fever, but I feel much better today. So even though everyone, I hope, is enjoying the spring break, I decided to record the video today, post it, and send an announcement on Brightspace along with the video link for you to watch it. This goes over two important sections of chapter 3, 3.1 and 3.2. 3.1 is on the limit definition. Video recording part 1 had a large group of examples. One of them was assigned to you. Hopefully you went over following the directions that were provided on part 1 of the recording. And then 3.2 is mainly focused, and 3.3 mainly focusing on basic rules of the first order derivative. As I'm going along, showing you examples, will be a variety of examples that I'm about to go over. I will go over and then review the basic rules of the first order derivative. Okay, so let me get started. So I'm going to go ahead and then share. I have a file that is halfway kind of like prepared. Okay, so let's go to, I thought Windows will do it. I do have the file. Okay, let's see if that's gonna allow me to see the file under the window option. There you go, I see it now. Okay, so now I'm sharing. As I said, the focus today will be on two major topics. Basic rules of the first order derivative and the limit at infinity, second part. So two topics. Limit at infinity and horizontal asymptotes. And then, as I said, basic rules of the first order derivative. Not all of them. As we go along the chapter 3, you're going to learn more basic rules, but we're going to focus on some essential ones, and that's always the good start. Okay, why limit at infinity? The last Wednesday, that was the last day that we had the class before the spring break. Class was canceled on Friday. As I explained to all of you, I had to attend the conference on Friday. But on that Wednesday, March 25th, I went over limit at infinity. And then at that time, I remember explaining two possible scenarios. Both of them are generated based on what we are trying to do with functions in general. So one scenario, your goal is to sketch the graph of the given function. You need to know what are the valid x's. When I use the word valid x's, that means if I plug it into the given function or the expression of f of x, I should be able to get the y. So at the center is always the order pair x comma y. Now, if I'm going to pick a value of x and then I'm not going to be able to find the y, then I'm running into the issues of generating the y through the limit process. So that's kind of like the whole idea behind limit. So I'm going to say find value of y using limit process. Okay, so that's kind of like the whole idea behind what we call it a limit process, and then explains why we use it. And let me color this or highlight this. I'm going to use blue to highlight it. Now there's two versions of this limit process. Both of them, again, are designed to give us all the possible scenarios of finding the y. So one scenario is x is approaching the center. Center is C. And then center C is a finite number. Finite real number. So this can be, when I say finite real number, it is well defined. But the y value computed through the limit through the limit process is not a finite number. So we're running into cases such as this one. I'm going to make this size 14 bigger for you. So we are running into the scenarios such as, let me break it right there. So that's kind of like, and then again, I'm going to highlight this. This time I'm going to highlight this using yellow. So we're running into the scenarios that look like this. So you find limit. As x is approaching C of the function f of x, and then you get infinity. And by the way, this can be both. So positive infinity, negative infinity. So it's not limited to just one scenario. This is a case where the y is infinity, as you notice, is not going to be defined. So you're still running into the scenarios of finding y to be undefined, infinity. And then in the previous video, you have well documented case of analytically, algebraically, graphically, showing the scenarios of x approaching a finite number, y infinity. Table approach ideally allows you to understand that. If that's the case, then limit does not exist, and the line, vertical in this case, and the vertical line, x equals c, is defined as vertical asymptote of function f of x, known as VA. And then I encourage you to look at all the scenarios that we discussed so you can kind of like review and then understand what I'm going over right now. So let me highlight this again using, or I can make a blue color, possibly one of those versions. Okay, there you go. This one looks better. Now, the second scenario that I'm about to discuss, and then you will see algebraically two breakdown examples. The second scenario is going to be a scenario where you're still finding the y, but take a look at how things are going to look like. So now what I'm going to do is I will copy and paste this to save some time and then apply the changes. So x is no longer going to a finite number, but x is going to infinity. And by the way, this can be positive infinity or negative infinity. So the center goes to infinity, and let me copy this right there. So center goes to infinity. I mean, x goes to the center, which is infinity. Oops. But the y value computed through the limit process is a finite number. So it's a finite number, we call it L. Then in this case, the limit, if the limit exists, in this case, the limit exists, and the horizontal line with the equation y equals L, which is the value of the limit, is defined as the horizontal asymptote of function f of x known as HA. We like to compute them algebraically. And in this particular case, we're going to run two scenarios of computing HA and computing the horizontal asymptotes for the given function algebraically. So here's case one. So we have the limit of the function as x approaches infinity. So you notice that x now is no longer going to a center that is a finite number, goes to infinity, of the ratio 2x over the square root of x squared plus 2. So this is our function f of x. So function f of x in this case is given find the limit at infinity and define the horizontal asymptotes by the equation of the form y equals L, where L is the value of the limit of function f of x as x approaches infinity. So let's look at the first one. I'm gonna make all of them different color. So that's direction. So now let's look at the first limit. So as I said, function f of x is 2x over the square root of x squared plus 2. We're taking the limit as x approaches infinity. We're going to use the algebraic approach in this case. Normally what you do is you use the idea of factoring out. Now this can be done by using the table approach as well. So I'm going to try to factor out the top expression and the bottom expression, I noticed that at the top I can only separate the 2 and x, but at the bottom I'm going to factor out an x squared. Anytime we factor a common factor or take out a common factor, in order to find the remaining factors, we need to divide each term, that in this case is inside the square root, by what I'm taking out. So each term will be divided by x squared inside parentheses. So the first term, so I just took out x squared. The first term x squared is divided by x squared, plus the number 2 is divided by x squared. In the next step, I'm going to keep the top as it is. X squared is taken out in front of the grouping symbol. Division of x squared by itself, you generate 1, not 0. And then I won't be able to do anything about 2 over x squared. So that's going to stay as it is. Now, what I did with this, I was able to create a product inside the square root. So created the product of the form AB inside the square root. If that's the case, you can distribute the square root. So you can write this product as the product of square root of the first term times square root of the second term. This can be done when you divide the 2 terms or when you have a fraction inside the square root, but it is not true for the difference between 2 terms or the sum between the 2 terms. So what I'm saying is if I have the square root of a minus b, this is not equal to square root of a minus square root of b. Or if I have the sum between a and b, the square root of a plus b is not the same as square root of a plus square root of b. So the square root can be distributed over product and quotient, cannot be distributed over the difference or summation. Let's go back. So I created a product, and that's the reason why I had to factor out. Because initially I had the square root of x squared plus 2. And then if you're thinking, oh, I can break this down as square root of x squared plus square root of 2. That is incorrect. You cannot distribute the square root over the summation. So therefore, you need to create an opportunity inside the square root to factor a common factor, generate the product, then factor out. And that's what I did by factoring out x squared. So now I have a product between x squared and then the expression inside parentheses. So that means I can split it up. I can take the square root of x squared multiplied by the square root of expression 1 plus 2 over x squared, which is the expression inside parentheses. And square root of x squared is x, which will be canceled out with the x at the top. And then you notice it's highlighted to show that those are common factors, so you can cancel them out. Now what's remain for us shows us that, okay, so it's 2 over 1 plus 2 over square root of 1 plus 2 over x squared. So we are replacing x by infinity. That becomes 2 over square root of 1 plus infinity square is just a fast-paced growing, becoming larger. So therefore, can be replaced again by infinity. It's just fast-paced going to infinity. And then a number that is finite over an extremely large number, when you divide it by denominator that is extremely large, that goes to 0. So as we move forward, anytime you see this a finite number such as 2 divided by infinity, you replace it by 0. So that becomes 2 over the square root of 1 plus 0. And square root of 1 plus 0 is square root of 1, which is 1. So that's 2 over 1. The answer is 2. So the limit is 2. The value 2 represents L. So we are under the condition of having a limit of the function f of x, x goes to infinity, that is equal to a finite number L, which is 2. Automatically, that number L will be used to define the horizontal asymptote. Be very careful when you define the horizontal asymptote. Why? You cannot just write the horizontal asymptote, in this case is 2. You have to write it as an equation in the form of y equals right there. So y equals L. So y equals a number. And then to finalize it, I'm writing the horizontal asymptote in this case for the function f of x is y equals 2. Okay. Hope the explanation is clear for everyone. Let's transition into another one. Again, limit at infinity. What is interesting about this example is the way it is designed. It is designed as a summation of 2 parts. So the first thing we need to do first, we need to separate those limits. So there are 2 terms connected by addition. So I'm going to take the limit of number 2 and then take the limit of the ratio. If you're taking a limit that does not depend on x, such as number 2, we call it the limit of a constant. X can go anywhere. That's not going to affect the value 2 because 2 does not have an x. So therefore, the limit of a constant stays as a constant. A constant means a number that does not depend on x. Doesn't really care where x is going. So the first limit is just 2. Now we have to focus on the second one. So the limit as x goes to infinity of x squared over x to the fourth plus 1. Again, we start with the process of factoring out. Always we factor out the powers, the variable x with the highest exponent. At the top, I won't be able to do anything. But at the bottom, I have to factor out x to the fourth, which is x with the highest exponent. And what this does allows us to find the remaining terms in the denominator by simply dividing them by x to the fourth. So we divide x to the fourth by x to the fourth by itself, and then 1 by x to the fourth when we factor out x to the fourth. So that becomes, don't forget the 2, which is the first part of the limit, was the limit of a constant, which we already computed. We're done with that. Carry over 2. Plus, then we get limit of x to the second over x to the fourth that is multiplied by this quantity. The quantity inside parentheses represents what remains after taking out as a common factor x to the fourth. Now, x squared means there's 2 x's at the top. X to the fourth at the bottom, that is outside parentheses, means there are 4 x's in the denominator. So both of them have 2 x's in common. So we get rid of x squared. That becomes 1, not 0. And then the bottom has an x squared outside parentheses. And the expression inside with the remaining terms becomes 1 plus 1 over x to the fourth. So we have 2 plus. Now I'm ready to substitute to find the limit. So we have 1 over infinity squared, and then 1 plus 1 over infinity. 1 over infinity is 0. So we have 2 plus 1 over infinity, and then 1 plus 0 is 1. So that's 2 plus 1 over infinity times 1, which is infinity. We have infinity in the denominator, and then 1 over infinity, that's a 0. So we get 2 plus 1 over infinity, which is 2 plus 0. The answer is 2. So in this case, the limit at infinity does exist, and it is equal to a finite number. Therefore, the line y equals 2, remember, we have to write the equation in this form, is the horizontal asymptote of this function. And these are all the examples that define precisely the limit at infinity, and then the explanation of finding algebraically limit at infinity. So let me save this. I'm going to save it as a PDF file, post it in Brightspace, upload this video so I can generate a link, and then again today at some point I'm going to create the video for the topic number 2, basic rules of differentiation, and then you're going to have a full picture of everything that was supposed to be covered prior to the spring break in that during the class on Friday. But we have most of the work done, so now the remaining portion is just the part of the basic rules of differentiation. So let me generate this video. I'll post the link, and then what I'm going to do is I will stop the sharing, stop the video right now. I'm concerned about the length of it, and then create another recording, part number 3, that is going to be only focused on the basic rules of differentiation. So thank you for watching this. One more video recording. Okay.